User and group ID numbers. In this video, we are going to see about user and group ID numbers. In Unix, with the exception of a few special system processes, processes are generated by users, that is root and otherwise, who have logged onto the system. During the login process, the system queries the password file to obtain two identification, that is ID numbers. The numbers the system obtains are in the third and fourth fields of the password entry for the user. These are respectively the real user ID, that is UID, and real group ID, that is GID for the user. For example, in the same password file entry, the user login ggluck has a real user ID of 1025 and a group ID of 1001. The real user ID should be, that is, if the system administrator is on the ball, a unique integer value, while the real group ID numbers should map to the group names stored in the files /etc/group. In general, IDs of less than 500 usually, that is but not always, indicate user logins with special status. For every process, the system also keeps a second set of IDs called effective IDs. The effective user ID, that is EUID, and effective group ID, that is EGID. The operating system uses the real IDs to identify the real user for things such as process accounting or sending mail, and the effective IDs to determine what additional permissions should be granted to the process. Most of the time, the real and effective IDs for a process are identical. However, there are occasions when non-privileged users on a system must be allowed to access or modify privileged files, that is such as the password file. To allow controlled access to key files, Linux has an additional set of file permission known as set user ID, that is SUID, and set group ID, that is SGID, that can be specified by the file's owner. When indicated, these permissions tell the operating system that when the program is run, the resulting process should have the privileges of the owner or group of the program, that is, versus the real user or group privileges associated with the process. In these instances, the effective IDs for the process become those indicated for the file's owner. A listing for SUID program follows. As shown, this password program, that is the executable for the system level command password, has its owner permissions set to RS. The letter S in the owner's category, found in place of the letter X, indicates that when this program is run, the process should have the privileges of the file owner, that is, which is root. The set user information is stored by the system in a 10th permission bit and can be modified using the system level command chmod. The SUID setting for the password program allows the non-privileged user running it to temporarily have a root, that is super user privileges. In this case, the user running the program will be able to modify the system password files as the permissions on the password files indicate that they are owned and can only be modified by root. Needless to say, programs that have their SUID or SGID bit set should be carefully thought out, especially if the programs are owned by the superuser, that is root. At a system level, the command ID displays the current user, group ID, and group affiliation information. Note that while a file can belong to only one group, a user can belong to many groups. The /etc/password file. In this video, we are going to see about the /etc/password file. The /etc/password file contains user account information. Each entry has several fields separated by colons. Everyone has permission to view the file's contents, that is sometimes referred to as a world-readable file because everyone can view it. Username, password, user identifier, that is UID, group identifier, that is GID, GECOS, home directory, shell. Username. The field contains the name of the user enters to log in. Using a combination of uppercase and lowercase letters is possible, but OpenSUSE recommends using lowercase letters because some mail exchange protocols don't respond to usernames containing uppercase letters. Password. This field contains the user's encrypted password that is represented by X in the preceding example, stored in the /etc/shadow file. If there is no /etc/shadow file, the actual password is stored in the /etc/password file. User identifier, that is UID. The user identifier, that is UID, is a unique number representing the username. Regular users typically have a UID greater than 100 because numbers less than 100 are reserved for system accounts, that is, which are non-user account typically used by services such as www and FTP. The root UID is 0. Group identifier, that is GID. The group identifier, that is GID, is a unique number that corresponds to each group. In the /etc/password file, that group is the user's primary group, which is the group owner for all new files the user creates. User can be assigned to multiple groups, but they can have only one primary group. GECOS. This optional field, that is, which stands for General Electric Comprehensive Operating System, an old OS used on mainframes, is used to store additional user information such as the user's full name. Home directory. This field lists the absolute path to the user's home directory. Shell. This field specifies the default shell that starts when the user logs in. The /etc/shadow file. In this video, we are going to see about the /etc/shadow file. The /etc/shadow file is configuration file containing passwords and password expiration information for all user accounts. It can be read only by the root user. The following list explains each field that is separated by the character in this sample entry in the /etc/shadow file. Username. This field contains the name of the user enters to log in. Encrypted password. This field stores the user's encrypted password. Last password change. This field represents the number of days since January 1, 1970 that the password was last changed. In the example, the number 14743 translates to 14,743 days since January 1st, 1970. Minimum. This field specifies the number of days before the password can be changed. The value 0 in this field means the password can be changed anytime. Expiration. This field shows the number of days before the password must be changed. The value 99999 in this field means the user's password never expires. Warning. This field represents the number of days remaining until the password must be changed. For example, the value 7 in this field means the user gets a warning message a week before his or her password expires. Disabled. This field contains the number of days after a password has expired until the user account is disabled. No entry in this field as in preceding example means that account is disabled immediately after the password expires. Disabled data. This field specifies the number of days since January 1st, 1970 that the account has been disabled. No entry in this field as in the preceding example means the account hasn't been disabled. Reserved. This field isn't currently in use. It's been reserved for future use. The/etc/group file. In this video, we are going to see about the/etc/group file. The/etc/group file is a configuration file that stores group information and can be read by everyone on the system. The following example shows an entry in this file followed by a description of each field. Video X33 Dustin Student 1. Group name. This field shows the group's descriptive name rather than the GID. Password. This field contains the group's encrypted password. Typically, a group password isn't used, but if one is set, other users can join the group by using the new group command. Group identifier, that is GID. This unique number represents the user's primary group. List of members. A list of group members, each member is separated by a comma. User management tools. In this video, we are going to see about user management tools. The wonderful part about having password database files that have a well-defined format in straight text is that it is easy for anyone to write their own management tools. Indeed, many site administrators have already done this in order to integrate their tools along with the rest of their organization's infrastructure. They can start a new user from the same form that lets them update the corporate phone and email directory, LDAP servers, web pages, and so on. Of course, not everyone wants to write their own tools, which is why Linux comes with several existing tools that do the job for you. User management tool that can be used from the command line interface as well as graphical user interface, that is GUI tools. Of course, learning how to use both is preferred route since they both have their advantages and place. System users and groups. In this video, we are going to see about system users and groups. The webmin module users and groups that is found under the system category as shown in figure can be used to create, edit and delete all the Unix users and groups on your system. You should always be careful when using this module to edit existing system users like root and daemon because changing or deleting them could stop your system from working. Some users have their home directory set to /the root directory. Deleting such a user would cause all the files on your system to be deleted. Monitoring logins. In this video, we are going to see about monitoring logins. In order to work on a Linux system directly, you will need to provide a username and password. You always need to authenticate to the system. Linux systems have two basic modes for a system to run in, either quick and sober in text console mode, which looks like DOS with mouse, multitasking and multi-user features, or in graphical mode, which looks better but eats more system resources. Graphical mode. Connect to the system using graphical mode when you are first asked for your username and then in a new window to type your password. To log in, make sure the mouse pointer is in the login window. Provide your username and password to the system and click OK or press enter. After entering your username/password combination, it can take a little while before the graphical environment is started, depending on the CPU speed of your computer, on the software you use, and on your personal settings. While browsing the menus, you will notice that a lot of things can be done without entering commands via the keyboard. For most users, the good old point n-click method of dealing with a computer will do. But this guide is for future network and system administrators who will need to meddle with the heart of the system. They need a stronger tool than a mouse to handle all the tasks they will face. This tool is the shell, and when in graphical mode, we activate our shell by opening a terminal window. The terminal window is your control panel for the system. Almost everything that follows is done using this simple but powerful text tool. A terminal window should always show a command prompt when you open one. The terminal shows a standard prompt which displays the user login's name and the current working directory represented by the tilde. Text mode. In the text mode, when the whole screen is black, showing, that is in most cases, white characters, a text mode login screen typically shows some information about the machine you are working on, the name of the machine and a prompt waiting for you to log in. The login is different from a graphical login in that you have to hit the enter key after providing your username, because there are no buttons on the screen that you can click with the mouse. Then you should type your password followed by another enter. You won't see any indication that you are entering something, not even an asterisk, and you won't see the cursor move. But this is normal on Linux and is done for security reasons. Default permissions. In this video, we are going to see about default permissions. Default permissions are set when creating a new file, and these permissions are determined by the umask setting. This is a shell setting that is set for all users when logging into the system. The default umask makes sure that all users have read access to all new files. Because this isn't very secure, it makes sense to restrict the default umask a little. A numeric value is used in the umask setting, and this value is subtracted from the maximum permissions that can be set automatically. The maximum setting are 666 for files and 777 for directories. Of course, some exceptions to this rule make it all quite hard to understand, but you can find a complete overview of umask setting. Of the digits used in the umask, as with the numeric arguments for the chmod command, the first digit refers to user permissions, the second digit refers to the group permissions, and the last digit refers to the default permissions for others. The default umask setting for 022 gives 644 for all new files and 755 for all new directories that are created on your server. You can change the umask setting for all users or for individual users. If you want to set the umask for all users, you must make sure that umask setting is entered in the /etc/profile configuration file. If the umask is changed in this file, it applies to all users logging into your server. An alternative to the umask in /etc/profile is to change the umask setting in a file with the name profile that is created in the home directory of an individual user. Setting applied in this file are applied for only the user who owns the home directory, and so this is a nice method to create an exception for a single user. For example, create a profile in the home directory of the user root, and in there apply the umask setting for 027, whereas the generic umask setting for ordinary users is set to 022 in /etc/profile. Special permissions for executable. In this video, we are going to see about special permissions for executable. Linux offers three types of special permission bits that may be set on executable files or directories to allow them to respond differently for certain operations. These permission bits are set UID, that is set user identifier bit, set GID, that is set group identifier bit, sticky bit. The first two bits may be defined on executable files to provide non-owners and non-group members the ability to run executables with the privileges of the owner or the owning group, respectively. The set GID bit may also be set on shared directories for group collaboration. The last bit may be set on public directories for inhibiting file deletion by non-owners. The use of the special bits should be regulated and monitored appropriately to avoid potential security issues to the system and applications. Permissions. In this video, we are going to see about permissions. The Unix operating system, and likewise Linux, differs from other computing environments in that it is not only a multitasking system, but it is also a multi-user system as well. It means that more than one user can be operating the computer at the same time. While your computer will only have one keyboard and monitor, it can still be used by more than one user. For example, if your computer is attached to a network or the internet, remote users can log in via Telnet or SSH, that is, secure shell, and operate the computer. In fact, remote users can execute X applications and have graphical output displayed on a remote computer. The X Windows system supports this. The multi-user capability of Unix is not a recent innovation, but rather a feature that is deeply ingrained into the design of the operating system. A typical university computer system consisted of a large mainframe computer located in some building on campus, and terminals were located throughout the campus, each connected to the large central computer. The computer would support many users at the same time. In order to make this practical, a method had to be devised to protect the users from each other. After all, you could not allow the actions of one user to crash the computer, nor could you allow one user to interfere with the files belonging to another user. Some commands: chmod modify file access rights, su temporarily become the super user, chown change file ownership, chgrp change a file's group ownership. Directory permissions. In this video, we are going to see about directory permissions. The chmod command can also be used to control the access permissions for directories. In most ways, the permissions scheme for directories works the same way as they do with files. However, the execution permission is used in a different way. It provides control for access to file listing and other things. Here are some useful settings for directories. Value, meaning 777. That is RWX, RWX, RWX. No restrictions on permissions. Anybody may list files, create new files in the directory, and delete files in the directory. Generally not a good setting. 755. That is RWXR, XRX. The directory owner has full access. All others may list the directory, but cannot create files nor delete them. This setting is common for directories that you wish to share with other users. 700. That is RWX. The directory owner has full access. Nobody else has any rights. This setting is useful for directories that only the owner may use and must be kept private from others.